Thanks, Ravi. Thanks for the intro. Thanks, John, Belen, Eva, for organising QPL. Thanks for inviting me to come and give a talk at 9 a.m. on a Wednesday. I said one condition, if I was going to agree to give a talk at QPL, I said one condition is that in my GatherTown space, you put a chaise longue, a digital chaise longue, and I would like to thank the organisers for meeting that request of putting a digital chaise longue in my digital space. So thanks again for that. I don't make many requests, but this was one of them. Okay, so if you're watching this on YouTube in a month, don't forget to like and subscribe. QPL can thank me later for that. Okay, so today I want to talk about how quantum networks can self-test all pure entangled states. And this is joint work with Ivan Šupić, Joe Bowles, Marc-Olivier Renou, and Antonio Thien. Ivan's at Lip 6 in Paris, and the other three are at TIC4. Okay, so, right, I hoped to be giving this talk with a paper on the archive. But yeah, yes, it's not on the archive yet. It should be appearing on the archive soon. So I think this tempered a little bit what I'm going to cover in the talk. And at times when I was arranging things, I realized this was turning into a bit more like a tutorial than a talk. But yes, I'll be setting things out, and then at the end, I'll be discussing some more recent work that we've been working on. Okay, but first I'd like to give an informal overview. So imagine we've got these two devices, and these devices have inputs and outputs. Okay, so you select X from some finite set, big X, you plug it into your device and you get some output A. And likewise for the other device. And we're assuming that these devices can behave according to quantum theory. So we can assume that they have some shared quantum state rho. Okay, now we just have access to these black boxes. We can plug in classical data and get classical data out, but we don't know what the dimension of the Hilbert spaces are. Okay, we don't know the dimension of the Hilbert space corresponding to rho, nor what's inside each of the boxes. Because classical data is being generated with these devices, we can assume there's some sort of measurement going on, but we don't know what the measurements are that are being made. And because we fundamentally don't know the dimension of the Hilbert spaces, we also don't know what the joint quantum state is. So what do we know? Well, we get access to some statistics, right? We keep using these devices, we plug in inputs and we get outputs, and we can generate some statistics, some probabilities. So we've got P of AB given XY. Okay, formally we have P is A equal to A, B is equal to B, conditioned on X equal to X, Y equal to Y. But yes, so I'm going to be shortening that to P of AB given XY. Okay, so we're given these probabilities, and given these probabilities, we want to conclude something about this shared quantum state here that the two parties have access to. So this is a bit like a reverse Born rule, right? So in the normal Born rule, you're given your quantum state, you're given your measurements, and then from that you can obtain your probabilities. Here we're given the probabilities, and we want to go back and say something about the state shared by the two parties. So this, in a very informal, loose way, is pretty much the drive of self-testing, kind of thinking about this reverse Born rule. So when we say correlations self-test a particular quantum state, what we're saying is these correlations allow us to conclude that up to some symmetries, this state is shared by the parties. So this state is inside this box. Okay, so given these correlations, if they can self-test a particular quantum state, this means we can conclude up to symmetries that this state is kind of lurking within these boxes. Okay, so that's kind of traditional self-testing. You want to make a statement about the quantum state shared by all of the parties, given access to the statistics from all of the parties. In our work, there's a little bit of a different angle on self-testing, where we consider things a bit more general than this, where we can have n parties. So in the example on the left, we've got 5 black boxes. So we've got 5 parties. Again, each party plugs an input into their box and gets an output. And you can generate n-partite statistics. The thrust of this talk is going to be trying to address the question of what can we conclude about the quantum state shared by some or all of the parties. So we're given statistics for n parties, and can we conclude something about the quantum state shared by some of the parties? Okay, and we call this network self-testing. So network because we've got a bunch of devices, and you can imagine they're all networked together. They're sharing some resources, and within this network, we want to say something about the quantum state. Okay, so we say the n-partite correlations network self-test a particular m-partite quantum state where m can be less than or equal to n. If we can conclude, again, up to some symmetries, this state is shared by that m parties. Okay, so this is the kind of scope of the talk, but we'll get to that. And so our result is informally that for every finite dimensional pure m-partite entangled state, so throw as many acronyms as you want at it, there exist 2 m-partite correlations that network self-test that state. Okay, so we have a network of 2 m parties, and we look at the correlations generated by this network of 2 m parties, and we can conclude something about a quantum state shared by m of those parties. Okay, so my plan in the next 15 minutes is to introduce self-testing with a bit more care, discuss some of the caveats, give a broad overview of the main results in self-testing. Naturally, I'll probably miss out some very key results, but I wanted to pinpoint some of the important results, especially ones that we're going to be using in this work. And then I want to get on to talking about network self-testing, more formally describe the result above about self-testing m-partite entangled states in a network of 2 m parties. And I'm going to give a rough proof sketch, and hopefully I don't run out of time whilst giving this proof sketch. Okay, so I've kind of stated what the problem is very loosely. QPL loves foundational research, so I probably don't need to push too much the goal of just answering questions for the sake of it. But, there is a motivation for studying self-testing. So one of these motivations is in quantum information. So self-testing is a primitive for many protocols in device-independent quantum information, such as randomness expansion, where you start with a small amount of randomness and you use quantum devices to make more randomness. And things like delegated quantum computation. So you can imagine you have some distant quantum computer that you can only interact with classically, and you want to delegate a quantum computation to that computer, and you want to verify it's doing the right thing. So self-testing is really useful in that context. And so broadly speaking, device-independent quantum information it's, you know, it's very apropos to this black box setting, because in device-independent quantum information, one only has access to the classical data produced by the black boxes and the statistics you get from that. I guess more foundationally, self-testing has a nice connection to the study of the geometry of quantum correlations in Bell scenarios. So if you want to characterize the set of quantum correlations that you get from a Bell test, you know, self-testing is very much related to this area of research. Okay, and more broadly, talking about self-testing, there's been some very nice recent work by Miriam Weilenmann and Roger Kolbeck on self-testing physical theories. So this is where you take this black box setting and you want to rule out certain physical theories within a black box setting. So in this talk, I will be assuming that everything has a quantum description, but I think this is a really nice, interesting research direction. Okay, and if my self-testing primer, my introduction to self-testing, leaves you wanting clarification or more, I think there's a really excellent review that was published in Quantum by Ivan Šupić and Joe Bowles. Yes, they are my co-authors on this paper, but it is genuinely, yeah, sorry, they're my co-authors on this work that I'm talking about today, but it's really a very good review, so I recommend it. Okay, so let's get on to the self-testing primer. So, you know, with anything, there are background assumptions. So we should state clearly what the background assumptions are. So as I said a second ago, we assume that devices can be realized with quantum systems. So there's some quantum state, there are some measurements that are producing the classical data. And every time you plug in data into your device and get data out, we assume this is a single round of an experiment and it's IID, so independent, identically distributed. And so this means that the same quantum state is being produced in each round and the same measurements are being made. Okay, the same measurement apparatus is being used. There may be different measurement outcomes, but the same kind of apparatus is being used, depending on X and Y. Okay. And the devices don't permit any hidden form of communication or any obvious form of communication. And importantly, the inputs to the device, X and Y, are chosen independently of the experiment. So you've got some process that generates X and Y for you, and you plug that into your devices. And that process to produce X and Y is independent of what is in the experiment. So if I can distill all of those background assumptions into a claim, it's that my experiment involves sharing some quantum state rho. So I'll abuse notation here and refer to this as rho AB. So this is party A, this is party B, and they're sharing some state rho AB. And this party here is making a measurement here, and this party here is making a measurement here. And without loss of generality, because we don't know what the dimensions are of the systems, we can take these measurements made by these two parties to be projected measurements. So that's just what's being said here. I've got pi A given X, pi B given Y. They're linear operators acting on the Hilbert space A and B, HA and HB, and these are projective measurements. Okay, good. So another without loss of generality is, instead of having this mixed state, which we had in the previous slide, shared between the two parties, we can consider a pure state. So we can take whatever state there is between A and B and introduce a third system E, which is like the purification of that system. So rho AB can always be taken to be, you know, what you get from doing the partial trace over E of the state psi ABE. Okay, so then we can, you know, simplify things again and introduce an identity operator on this purified system and some projective measurements on the other two systems. And in the self-testing literature, this is referred to as the physical experiment. So this is what's going on inside the device. It has a description, which is this psi and pi's. Okay, this is what's going on inside the device. Okay, and I'm going to be drawing lots of pictures because it's QPL and it's the morning and I love drawing pictures. So, you know, I can draw a picture saying that I've got some state over three systems, A, B, and E. And I'm going to trace out this third system, and I've got some effects acting on my systems A and B. And when I start drawing diagrams, things are going to be a little bit confusing in that when I draw these kind of circuit diagrams, time's going to go upwards. When I talk about boxes, things are going to go a bit downwards. Maybe it's just a sign of my general confusion. I know, Ross. Whoa, indeed. So yeah, good. Right. So the objective of self-testing is to relate the physical state to some target state. Okay. So we've got our physical experiment and I want to relate this to some target state. This is the thing that I want to self-test ultimately. I want to self-test that my device has something like the target state. Okay, now there are obstacles to concluding what the state is if you're just given the correlations. So a more obvious kind of constraint is if I apply a local unitary to the A system and a local unitary to the B system, and then before I make my measurement, I kind of apply another unitary that undoes the original unitary, right? This gives me exactly the same statistics. But now the issue is, okay, I was trying to self-test maybe a particular state here, but now I've got another state over here, phi. So this is, you know, an obstacle to saying what the exact state is that the parties are sharing, because you're allowed this freedom in the local unitaries. And these unitaries can be applied to the states and the measurements. Okay. Another obstacle to concluding what the state is from the correlations is that you can have additional trivial degrees of freedom, right? I can start with my state on the left and my measurements, and then I can start bringing in extra, what's the technical term? Stuff, and trace it out, right? And this produces exactly the same statistics as the thing on the left. I'm just introducing some extra auxiliary systems and then tracing them out, right? And then, okay, you know, the state that's being shared by the two parties could be something on the form like this, right? Where I have two auxiliary systems, they're in the state 0, 0. Okay, so these are two obstacles to concluding what the state is inside the box. And a really nice way to think about these local operations of the local unitaries or introducing additional degrees of freedom is to think of them as free operations, right? You know, I've got my devices which are localized and I can, you know, I have some freedom in the kinds of local operations I can do on these systems inside the device. So they're free operations, they can be implemented locally. Okay. So I have to think about these free operations which can interconvert between states. And another general set of free operations are local isometries, right? Okay, so local isometry encompasses these things, and that I can bring in some additional system, additional degree of freedom, prepare it in some fixed state, and then interact this additional auxiliary system with my initial system, right? I can apply isometries to my physical experiment. And these local isometries kind of leave the statistics invariant. An important thing to point out at this point is that this purifying system isn't touched. So this because, you know, it's external to what's inside the devices. So there's nothing acting on this purifying system. It's inaccessible to the experiment. Okay, so when we say that some statistics, some correlations that are observed in an experiment self-test a pure state, we're saying that there exist local isometries on the local systems here. There exist local isometries that when I apply these local isometries, phi A and phi B, to the shared state, I get my target state here, psi prime, and some junk, some stuff that's left over on the side. Excuse me, sorry about this. Okay, so pictorially, that means that if I've got this shared state here, I apply my local isometries on these subsystems. Then this isometry, if the correlations self-test the pure state psi prime here, then this isometry will take me to something that looks like this. Right, I've got this target state psi prime, and then I've got some additional junk. And part of the junk could be in one laboratory, and another part of the junk could be in another laboratory. Okay, so this is what we mean by self-testing. So you can think of these local isometries. These are the local operations that map the physical state inside your experiment to the target state. And it's really important to say that these local isometries are just mathematical constructions. It's not what's happening inside the device. It's purely a convenient mathematical construction for us to conclude what's inside the box up to these symmetries. So it's not necessarily what's happening inside the device. It's just a mathematical construction that allows us to conclude something. Okay. And in the literature, instead of just looking at the pure correlations, it's very common to look at Bell inequalities instead. Okay, so you've got a Bell inequality of this form, you've got your correlations, you've got some real numbers, and then if these correlations satisfy low-code invariable theory, then this is upper bounded by C. And then quantum systems can violate these bounds. Okay. So often you'll see self-testing from Bell inequalities where if we're given a Bell expression value, such that when I evaluate this Bell expression for my statistics, it's equal to some value Q, I say this Bell expression self-tests the pure state psi prime, again, if there exist local isometries. So you can see this is a nice relaxation of the original problem of just given all of the correlations. Instead, here we have this Bell expression. Okay, so what are the main results in self-testing? Well, so far we've looked at just two systems. So let's talk about self-testing of bipartite pure states. So most of the literature is concerned with pure states. There's an interesting discussion to be had about mixed states, but for simplicity, I'll just keep to pure states right now. So self-testing, you know, as a terminology and as a framework was first defined by Myers and Yao in 2004, where they showed that the 2-qubit maximally entangled states can be self-tested. Okay. But interestingly, independently, and going back to the, the 80s, it was shown that if you have Sirelson's bound, or the maximal violation of the Clauser-Horn-Shimoni-Holt inequality, this also self-tests the 2-qubit maximally entangled states as well. So yes, there was a kind of a long history of this problem that's been discovered and rediscovered by many people. Most recently, in terms of bipartite pure states, there was this really nice general result by Coladangelo et al. where they showed that all bipartite entangled pure states can be self-tested. Okay, so that pretty much ties everything up in the bipartite case. If you're trying to self-test, if you're trying to self-test a bipartite pure entangled state, it's doable. There is a recipe out there. There is a prescription. So I think Alex just asked the question: do you typically need one Bell value or many? So Alex, are you asking about? So if I have one Bell expression, do I only need one Bell expression to evaluate for one particular value? So hopefully this slide answers this question, that you can, with one particular Bell inequality, the Clauser-Horn-Schimoni-Holt, CHSH, you can self-test 2-qubit multiple maximally entangled states. So actually in our work, you do require the violation of multiple Bell expressions. So whilst for the simple cases, you might only need one, in our case, we need multiple Bell expressions. I hope that answered the question. If not, I'll come back to it later. Okay, and since Ravi is chairing, well, actually, no, I think this is a really nice paper, but I don't want to upset the chair, especially when they've got their camera turned off. There is a more general notion of self-testing, which is addressed in this paper here at the bottom by David Schmidt et al. So, we discussed some local operations which can be seen as free operations within this framework, so they can be implemented locally. And you can see, if we're talking about free operations, we're really couching things in terms of a resource theory. And so, if you're talking about, localized measurements on some joint state, the relevant resource theory you can think about is local operations and shared randomness, so LOSR. So you can come up with a more general definition of self-testing to allow for the possibility that you have your physical state and there exists some LOSR operations that take it to your target state. So for example, this could allow self-testing of mixed states. So this allows for a more general definition.
I think at this point, maybe I'll ask a question that I was thinking
go for it, Ravi. Yeah.
Which was about, so you used the word phrase free operations at some point to describe the isometries. And I was wondering if in this paper you have a resource theoretic approach or something, or is it just in a vague sense?
Yeah, it's I think it's more of a motivational sense. It's not resource theoretic. It's okay. It's a nice way to think about it. Yeah.
Mm-hmm. Thanks.
That's all right. Okay. So I think this is really nice. Okay, local isometries are examples of local operations with shared randomness. But this is something that would be nice to think about in the future. So at the moment, it's a bit of a side. Okay. So in addition to self-testing states, I would also like to self-test measurements. This will be useful in our work. Now, instead of just self-testing a state by applying some local isometries, we now imagine that you're applying some projectors to the state and then applying some local isometries. And so we can say that our correlations now self-test pure state and measurements psi prime, ma given x and b given y. If there exist local isometries, again, here I've got my local isometries up here, such that phi a tensor phi b tensor identity on E applied to the post-measurement state, which could be subnormalized, can be rewritten as applying measurements to the target state psi prime and with some junk left over. So you've got something that looks like this. So this is really useful, right? That you now, you can say that the measurements in addition to the state are kind of well defined in a way, in that your measurements only act on this target state and they don't act on something else. So this is quite nice. And this is really useful for cryptographic applications. Okay. So a really useful result that we've, I just saw it as a comment. I think in the Cola-D'Angelo et al. Paper, or pure bipartite entangled states, eventually you'll need multiple Bell inequalities because you're essentially, yes, this is a very good point. Yeah. In that example, you consider breaking down your bipartite state into qubit subspaces, and you're kind of applying Bell inequalities on these subspaces. Yeah, thanks for that point. Yeah. So that's another example of where you're kind of using multiple Bell expressions. In that case, in general, you'll be using like tilted CHSH type things. Okay, so self-testing of states and measurements. I'm going to state this result because we use it in our work, and I think it's good to know that if you've got this shared state here, you've got some, and then you've got some measurements being made on the state, and you've got some local isometries. You can self-test n pairs of maximally entangled 2 qubit states and Pauli measurements. Sorry, that shouldn't be that. And n qubit tensor products of Pauli measurements can be self-tested. So you've got 2 parties, and the parties can share n pairs of maximally entangled 2 qubit states. And on each of the qubits, you can imagine making Pauli measurements. And we want to self-test this target state of sharing a bunch of pairs of maximally entangled states and making Pauli measurements from our physical experiment here on the left. So there exists an isometry where there exist local isometries, phi A, phi B, where you can basically end up with one party having a bunch of halves of maximally entangled state, which I'll represent as a cup here, and you've got some junk left over. Okay, so yeah, so this is a really nice general result that I think has been proven in a couple of ways. Okay, so that was all bipartite. So let's get on to the multipartite case. So the traditional definition of self-testing can be generalized to more than 2 parties, right? It should be pretty straightforward. You have n parties, they each make some local measurements on some shared state row, and you end up with n-partite statistics. Okay, and we're just going to go from having local isometries on 2 parties to now having local isometries on n parties. So we say the correlations, blah, self-test the n-partite pure state, which is on n systems here. So I've got n Hilbert spaces here, and we say the correlation self-test this n-partite pure state if there exist local isometries on each of these systems that take you to the target state and some junk. Okay, and here we've got an n-fold tensor product of our local isometries. So everything there just translate from the bipartite case to the multipartite case. And so we get something that looks like this, right? You just draw a bunch more wires. Okay, so what's known about self-testing of multipartite pure states? Okay, so a lot of nice things that occur in the bipartite case, the Schmidt decomposition, singular value decomposition, all of this, all of these nice things that you get in the bipartite case kind of go out the window when you start allowing for n parties. So it becomes a bit more of a wilderness to explore the self-testing of multipartite pure states. But nevertheless, there have been some really nice results. So McCaig in 2014 showed that graph states can be self-tested based on the stabilizers of graph states. Don't worry if you don't know what that means. And there was a nice general technique developed by Ivan Šupić. That name just keeps popping up. This nice technique, which uses projections onto bipartite systems, which then you can leverage to self-test multipartite systems. So this is a really nice general technique, and you can self-test families of states with this method. And previously at QPL, I guess 3 years ago now, there was this nice result by Briner et al. Where they self-tested many copies of a GHZ state between 3 parties. And a lot of their reasoning used categorical QM. So there are these nice general results that cover certain families of states, but it's still open whether all multipartite states can be self-tested in this scenario that I just described. And I think I saw something pop up in the chat. Just as a side question, do we trust the measurement devices? For example, what if some of these devices are just random number generators and they don't care about row? Yeah, so thanks for that. So we don't trust the measurement devices at all. They are complete black boxes to us. So there are some states shared between the 2 devices, and then there are some measurements happening inside the device, and this is all part of the physical experiment. But a priori, we don't know anything about this physical experiment. We don't know what measurements are being made. So if it were just a random number generator, for example, it wouldn't violate a Bell inequality, and we wouldn't be able to self-test the quantum state, for example. Okay, so it's open whether all multipartite states can be self-tested. So what we do to kind of resolve or, make a decisive step towards resolving this open question in the multipartite case is we, if you're not getting anywhere, you generalize, right? So what we do is we generalize the multipartite setting. So this was the setting we had before. Now, what we do is we consider, why not throw in some more parties whilst we're at it? So now we could imagine you've got these n parties here. So in this case, we've got 7 parties. And from the statistics given from these 7 parties or n parties in general, what we want to do is self-test the state on m parties. Okay, we want to conclude something about a state on a bunch of subsystems. Okay, and hopefully it'll become clear why we're introducing this more general definition. But okay. Here's the definition. So we have our n-partite correlations. We've got the correlations generated from n parties. And we say these correlations network self-test an m-partite pure state if there exist local isometries on the whole, on all n parties, such that you end up again with your target state, which is now an m-partite target state. So this is an n-partite physical state, and we want to get our m-partite target state. Okay, good. So this is our general definition of network self-testing. So we allow for freedom in that the number of parties doesn't necessarily correspond to the number of subsystems in the state that we're self-testing. Okay, just a quick note that we can limit ourselves to talking about our m-partite pure state being entangled across all possible bipartitions across subsystems. Otherwise, you can perform self-tests on the smaller states. That's just a side note. Okay, so I'm hoping this provokes a bit of discussion. But there is a bit of an obstacle for multipartite and network self-testing, and one issue is this obstacle is complex conjugation. So you've got your statistics over here on the left, and for any projective measurements, states like this, you can take the complex conjugate of the state and your projectors, and you get exactly the same statistics. So imagine you're looking at a device and you don't know if the state inside the device is psi or psi star, the complex conjugate. And yeah, okay, this is a bit of an obstacle because, taking the complex conjugate of a system is not a physical operation, so doesn't belong to our set of operations which could be freely performed. It's unphysical. So there are two options for this. You kind of live with this limitation, and you say, I can't distinguish between psi and psi star in general, and so you say, okay, this is just a limitation of the framework, and if we're being honest, that we shouldn't expect to be able to distinguish them. And another option that some people have taken, which is to amend the notion of self-testing. And this might appear in a perhaps ad hoc fashion, but it can be justified, I think. So in line with what's in the literature, what we do is opt for the latter, where we allow the possibility that the following state can be self-tested, where the auxiliary states keep track of the original or its complex conjugate. So now imagine you've got your M subsystems, and if this, for each M subsystem, if the state is 0, that means it's the original state psi shared amongst all the parties. And if it's the state 1 in all of the subsystems, that means the parties are sharing the complex conjugate of psi, and you're allowing for superpositions of this. Okay. So given a state of this form, we can make local measurements of this form, where basically you apply your original measurement if your auxiliary state is 0, and you apply the complex conjugate if it is 1. And this results in the same probability distribution as if we had the state or its complex conjugate. So this is a way of, kind of generalizing the framework a little bit to say, can we conclude from the statistics something that looks like this, which is a superposition of psi and its complex conjugate. Okay, and our main result is that for every M-partite pure entangled state, psi prime, that should be an M. So we've got an M-partite state here. There exist N-partite correlations where N is equal to 2M that networks self-test this state here. So given this psi prime, we've got psi prime star here. Okay, so we can self-test this superposition of psi and its complex conjugate. And notice if psi prime is real, then you just get kind of the state back. Right. So the structure for doing this is basically the following, where we have our inner circle corresponding to the state psi prime that we want to self-test. And we have a bunch of auxiliary parties outside this ring. Okay, so for each party corresponding to this a subsystem in psi prime, we've got another additional party, and that's where this 2M comes from. Okay, so that's the structure of the network that can network self-test this state. And in the time I've got remaining, I would like to give a proof sketch of this. So the idea roughly is to perform tomography on the quantum state that we want to self-test, this psi prime. And we want to perform tomography on this quantum state, even though it's inside a black box, by composing smaller systems that can individually be self-tested. So we can imagine you've got a bunch of boxes that you can start composing. And then if each of these boxes can be self-tested, then when I start composing things, I can self-test the whole thing. And I end up doing tomography on my quantum state. So that's the rough idea. So, I'm started talking about tomography, which is different from self-testing. So, and I'm talking about composing things. So let's talk about tomography through composition. So let's start with the setting without black boxes. I've made things green to mean it's got the green light. Okay, so everything is accessible here. An experimenter has direct access to the open wires. There's some shared state and there's some open wires. And in any quantum experiment, you can, if you've got access to these quantum systems, if you've got a tomographically complete set of measurements, you can perfectly characterize this state here. Okay, so you know, if you've got 2 qubits, then your tomographically complete measurements would be, say, the Pauli measurements locally on each subsystem. Okay, now what can I do? Well, I can start bending some wires, right? I can start thinking of this, you know, in process theoretic terms. I've got my wires here, and what I can start doing is bending my wires, right? So now I've got this lovely bent wire here. So I go from here to here, I bend my wires. Okay, I acquire some complex conjugation, but I end up with this structure in the middle. This looks very alert and this looks very limp. So it looks a bit sad, but go with it. And what this cap is basically the effect corresponding to the maximally entangled state. Okay. So now, instead of performing tomographically complete measurements on these 2 systems, I can perform tomography by preparing appropriate states here and making entangling measurements on these 2 systems here. So what I do is I can prepare Pauli eigenstates, for example. So these could be Pauli eigenstates. And I perform some entangling measurements here. And this allows me to recover the characterization of the system that I get over here. Okay, so by bending the wires, I don't lose anything. And then, okay, once I've bent once, I can, why not? I can just bend the wires again. So this wire that was coming down, I can bend it back. So now I have a nice, happy effect again. So I've gone from having a state and I've bent it back round to having an effect. Okay, just to warn you, this I would say is far too much bending for, so just don't, that's too much bending. Don't ever go that far. I think this is a reasonable amount of bending. Okay. So what was the point of this bending is to say that tomography can be performed by making tomographically complete measurements on 1/2 of maximally entangled state. So this is my tomographically complete measurement on 1/2 of a maximally entangled state. And then I make an entangled measurement on this with my state here. So I can perform tomography instead of this, instead of this manner, I can perform tomography in that manner instead. Okay. And now the idea to go from everything being open and accessible, the idea is we want to do the above, but now inside black boxes. So now we want to go from having access to all of these things to each of these elements of this primitive being inside black boxes here. So now some of the measurements are inside some black boxes and some inside other black boxes. Okay, so the first step is now to go from the thing on the left to the thing on the right by bending round. Okay, so now the question is, can we still determine the state without having direct access to it or the measurements made on it? So now we have, we can prepare systems here, but maybe we don't have access to the state or the measurements made on this part of the state over here. So now it's inaccessible to us. So we can plug in some quantum states into our device, but everything else is black box. And so we can rewrite the framework here of, in terms of boxes, where now instead of a classical input, we can plug a quantum state into our box. Okay. And we receive a classical output, A and B. So we can plug in quantum states and we get classical outputs. Okay, so that's where things have changed now from this previous black box setting. And so in some previous work with Ivan Šupić, I feel like this talk is more of a tribute to Ivan now. So with Ivan Šupić, Laia Domingo Colomer and Antonia Thien, we showed how you can do certification of devices given this setting of trusted quantum inputs. So yes, so you've got this setting over here. So what does it look like as a circuit? You've got some joint state prepared here. Part of it goes over to one box. and you've got a joint measurement on this state and your quantum input. This is the most general thing you can do. And if you can plug in a tomographically complete set of states, so the Pauli eigenstates for qubits, for example, for this Hilbert space here and here, then we can characterize this thing as a joint POVM, and we can perform tomography on this joint POVM between the two parties. Okay. And so, yes, so these are the properties of the joint POVM. I've got my state living in this Hilbert space and this Hilbert space, and then I've got a joint POVM that acts on these Hilbert spaces, and it's positive and sums to identity over all the outputs. Okay, this was bipartite. I've just kept it like this, so it's kind of easy to see what's going on, but this all generalizes to M parties. So here is my trusted quantum input here that's characterized, and then I can plug it into my device here. And I don't necessarily know what this is, nor do I know what this is. Okay. So in this paper, we showed that you can do self-testing of multipartite pure states in the following manner. So we say that this POVM, which you get from plugging in tomographically complete set of states into your device, certifies the n-partite pure state of this form, if again there exist local isometries which act on the system that's being plugged in, the trusted system, and your hidden system here. Okay, so we can certify that a POVM certifies a particular pure state if there exist local isometries such that you get the thing that you're after plus some junk. Okay. So you get something that looks like this. This is your isometry here applied to your system, and you can show if the POVM certifies this pure state, you end up with this at the bottom. And our main result from this paper was that for every pure multipartite entangled state, there is a POVM in this measurement device independent framework that certifies it. So you can come up with a pure multipartite entangled state, and I can give you a POVM that will certify that the two parties up to isometries share that entangled state. Okay, so that's the first step in this journey of going from this setting here with black boxes to inferring something about the state being shared here on the left. So now the second step is to go from having the case where I've got trusted quantum inputs here and here. So the point being was that in this previous setting, if we know what these states are here, we can conclude up to local isometries what the state is. So now we want to remove the need for these trusted quantum inputs. So we had a black box around these things, but not around these states. And what we would like to do is put some more black boxes around things. And how we're going to replace these trusted quantum inputs with something else is by bending the wire background. And then now we can treat this as bending around as an extra system that is a black box. It's now inaccessible to us. Okay. And so if I expand this out, what does this look like in this black box setting? Well, I now have 4 systems, and I want to self-test that these 2 systems here share maximally entangled state, which is what this corresponding to the bending of the wire is. And I want to self-test that these 2 systems share this maximally entangled state here. And if I can self-test that these 2 boxes share the maximally entangled state, and I can self-test that they make a particular tomographically complete measurements here, I have replaced my trusted quantum input here with something that's completely untrusted. Okay, so I'm leveraging some self-testing results to say something about tomography. Okay, so to quickly go over this second step, I require D copies of the maximally entangled 2-qubit state. because I can embed any maximally entangled state with enough copies of the maximally entangled 2-qubit state. And because this state can be self-tested along with Pauli measurements made on 1/2, this is enough to ensure that I am preparing Pauli eigenstates, for example, on the other system, and this will replace my trusted quantum input. Okay, there's a bit of work to do where you need to generalize this to like having D copies in parallel, but that's not such a problem. And the thing to point out is we don't actually initially assume any independence between these states. So there could be some joint state describing all of this behavior here, and we want to infer that there's a maximally entangled state here and a maximally entangled state here, and then psi here. Okay, so now by self-testing maximally entangled states, we can perform tomography up to isometries. So this is the final picture where I have for each system in my state that I want to self-test, I bring in an extra system and I self-test the maximally entangled state between this additional system and my main system. Okay, and I should definitely conclude now. So the whole point in this network self-testing approach is that we can show that any pure multipartite entangled state can be extracted from this network. So we go to a more general setting, and this allows us to conclude that it's possible to self-test any pure multipartite entangled state. And what I quite like about this is it's very compositional. So a lot of self-testing results rely on kind of algebraic results and things like this, whereas this is about composing smaller components with each other. And, to get the result, all we do is we can assume that the parties just share, all n parties share one giant quantum state. But actually, if you start imposing independence constraints, you can actually get nice, stronger results. And yeah, there's some open things, but I should definitely stop talking now. Thanks.